Well, final session. We've got three great speakers. We're going to start with Jeremy Singer. So Jeremy has been in Glasgow for the past 12 years of academic staff. He actually did his PhD in Cambridge, supervised by Martin Richards. I don't know how many people know Martin, who did the original language BCPL, well, actually B, and then B became C, and sort of things went on from there. So had a lot of influences on early language design. Anyway, Jeremy works on programming language, implementation technology, including compilers and virtual machines. Over to you, Jeremy.
Thanks, Simon. You could say that Cherry fixes all Martin's mistakes, perhaps, but yes, never mind. Good. So, hello, everybody. My name's Jeremy Singer from the University of Glasgow, and I am in a very comfortable position today. You know how normally you kind of go to a conference and none of your collaborators there and you get asked all the difficult questions? Well, today, everybody else from the team is here. So if there are any difficult questions, you can ask Jacob, Andre, Duncan, Dedgis, oh, he's not here actually, Laurie or Tom. Yes, so Jacob's from ARM, Laurie, Tom and Andre are from King's, and the rest of us are from Glasgow. And all our money comes from EPSRC, yay! Thank you, John, and everybody else from EPSRC, and we're very glad for all our support over the last 4 years. And you'll know, if you are a principal investigator of one of these DSBD grants, that every quarter, like clockwork, you get an email from EPSRC saying, fill in this report and tell us what your project is about and what it's been doing. And unfailingly, every quarter, we have copied and pasted this text into the box, or at least into the first box. Right, so I think John just kind of puts them in a filing cabinet, to be honest. I don't. Oh, right, okay, good. Yes, good. Okay, so maybe you only see the highlights. But yeah, here we go. So at least half of the top 10 languages run on virtual machines. Python, Java, C#, JavaScript, and PHP. Oh, but underneath those managed language runtimes is an implementation in C or C++. And VMs like Hotspot regularly have, Laurie plucked this figure from somewhere, 50 to 100 CVEs per year. So the Capable VMs project hypothesizes, here we go, Cherry enforced capabilities are the first realistic technique to make VM security proactive. Go Cherry. So really, our question is, why are virtual machines special? Why do we need lots of money from EPSRC to investigate capabilities on VMs? So you just think about that for a minute. What's special about virtual machines? Well, I love them because I've been hacking VMs since I was a PhD student. But why should you care about VMs? Well, I think VMs are exemplary code for featuring oodles of low-level platform-specific systems code. You know, all those kind of if-death cherries and if-death AOP64 and things, they're all packed inside virtual machines. Virtual machines feature increasingly large numbers of interactive runtime components. You know, you've got your allocator and your collector and your various levels of JIT compilers and your kind of green thread scheduler and everything else that's going on inside your runtime, all kind of interoperating. Virtual machines do lots of allocation and lots of cleanup, possibly garbage collection. And I think these memory-intensive aspects of VMs are particularly interesting for Cherry-based systems. Oh yeah, and there's runtime code generation going on as well. So data magically turns into code. We employed a case study-based approach to looking at capable VMs. So for each of these problems, we selected a particular VM from off the open source shelf and kind of peered into it and tried to, do capability things with it. So we have been looking at the MicroPython runtime. Now, I know some people here are working on kind of the big grown-up CPython runtime, but we started off with a baby MicroPython runtime. Hello, nice to see you. Yes, good. Well done. You've been working much harder than we have on CPython. We were looking at MicroPython, which is a much smaller scale Python runtime. And we think that exhibits low-level platform-specific systems code. We looked at the Lua interpreter. Well, actually, the folks at King's did this, so you can ask them all about it. And they are looking at compartmentalizing aspects of that runtime. We worked with the Bohm Demers Visor garbage collector and ported that to Cherry. And some people in our group have been looking at JavaScript core and JIT compilation inside that JavaScript engine. Again, building on work that's been done here at Cambridge. Okay, so those are our 4 case studies, which I am going to talk about just for the next few minutes. So low-level platform-specific code and MicroPython, first of all. Oh, help, I didn't know I did that. Ah, there is a new word in your dictionaries, maybe soon to appear in the Oxford English Dictionary, just in between check, C-H-E-Q-U-E, and cherish, C-H-E-R-I-S-H, is the word cherify. So we're all using that word now, aren't we? It's going to be, you know, word of the year, well, maybe not this year, but maybe next year, cherify. And cherification really is a thing. And lots of people have spoken about cherification already today. You know, people have been cherifying Rust or cherifying unikernels or cherifying lots and lots of things. You know, that idea of porting something to the Cherry kind of ecosystem and learning things about it is quite a specific porting process. You have to worry about, you know, word length assumptions. You have to worry about casts between integers and pointers. You have to worry about provenance and so on. And I think the claim is that cherification is, well, I wouldn't say it was entirely comfortable, but it certainly isn't too prickly. And there we go for KDE, apparently only 0.026% lines of code base needed to be modified for Cherry. So it's higher for systems code, maybe an order of magnitude more for MicroPython. We modified about 0.2% of the lines of code. And for memory allocator, like Microsoft's SNMalloc, 1%, so maybe an order of magnitude more of the lines of code needed to be modified. Oh yes, so cherifying really is a thing. Huawei thinks so anyway. Cherifying Linux, a practical view on using Cherry. So there we go. And yes, we have cherified MicroPython. Right, I really want to do a live demo, but I wasn't brave enough and I haven't got the setup here, but never mind. So imagine me typing this into my interactive Python prompt, import dodgy library. Okay, so I've got 2 byte arrays here. Where are they? Up there, yeah. And I'm just kind of poking bytes into them and I want them to say, oh, hello. So I'm going to print, oh, and then I'm going to call the dodgy library and I'm going to give it my first little buffer, my first little byte array there. And then I'm going to print the second byte array. And what happens after I call the dodgy library? Oh dear. So when I run this with just a standard AArch64 MicroPython, it says, oh, hack, because my string has been somehow intercepted and modified, even though I gave the dodgy library the reference to the tiny 1 byte array, somehow it's modified tiny 2. And the reason is because, of course, this is doing really dodgy stuff with C types and kind of offsetting from one buffer and finding another and searching for a particular value. And the worst thing is, you might not even be doing this with characters. You might be doing this with MicroPython bytecodes and injecting code into functions in your MicroPython code and then running those functions and something terrible's happened. So this is a dodgy library indeed. But if you run this with pure cat MicroPython, it says, oh, in address space security exception, which is much better. So we've got kind of tight bounds on our buffers here and we can't have these kind of space oddities or violations. When we started working on MicroPython, there were no CVEs reported for MicroPython, but since then there have been 2 which are to do with overflows and use after freeze, things that Cherry can mitigate. So, you know, MicroPython is becoming more prominent on the perhaps on the hackers' radar, and CVEs are being reported. We, incidentally, just to give you another anecdotal evidence of the value of Cherry, when we reported it, we found 2 memory bugs in MicroPython, which we reported and have been upstreamed to the main repository. Yeah. So I want to say this, and I think this is important. You know, everybody goes, well, you need to fix your pointer size assumptions, otherwise your code won't compile. But actually, there are some pointer size assumptions that aren't to do with correctness, but to do with performance. And we found loads of those in MicroPython and needed to fix those. And we got an order of magnitude speed up over our baseline MicroPython that compiled and ran over one that was kind of more optimized with the pointer size for 128-bit capabilities. Oh, I was really hoping I could tell you, where's Conrad gone? I was really hoping to tell you that you can say package 64C, install MicroPython, but sadly you can't. Thank you, Simon. But maybe soon you'll be able to. But you can certainly pull it from GitHub and you can build it on PureCap and compile it to PureCap. And we're currently working on a version for the Cherry at Ibex Core, and hopefully soon it'll be available on the Sonata board as well. Why are virtual machines special? Reason number 2, because they feature multiple interacting dynamic components. And the Lua interpreter is our case study here. Oh, so we learned another word, or perhaps an acronym. C18 is compartmentalization, Robert told us this morning. So I think compartmentalization is lightweight isolation. Instead of process-based isolation, now you're isolating just by having a sort of window onto the address space. And the size of that window is determined by your DDC, your default data capability, and your program counter capability. And then you need some kind of switcher to switch between these kind of windowed views of the address space. And for each compartment in which you're executing code, you perhaps need a local libc, and then you need some kind of clever tricks. And this is where my good friend Andre is mired in the slough of despond. Yes, sorting out dynamic loading and so on. And then you want to think about the compartment granularities. So do you want each function to live in its own compartment? Or do you want each shared object to live in its own compartment? Or do you want kind of user-defined compartment boundaries or some kind of automatically determined boundaries by analysis? So we're thinking about that, and yes, we don't necessarily have the right answers at the moment. In MicroPython, we are isolating at FFI call boundaries. So we're calling out external C libraries and building on the work of Dafeng and other people here as well. Good. Why are virtual machines special? Because they do lots of memory allocation and collection. So when you are trying to clean up during or after an allocation-intensive process, you'll need your root set of pointers from your stack and your registers and your global variables and so on. And then you'll need to trace through that root set to do a transitive closure of the object reference graph. And everything you can reach is alive and everything else can be thrown away. Scanning the heap becomes more complicated perhaps in a capability world, and moving objects and stitching up references to those objects becomes more complicated as well. So we looked at the BDWGC, the BOEM collector, and we've ported that, we've cherified that for both RISC-V and Morello. And again, very soon you'll be able to say package 64C, install BOEM GC perhaps. Good. So these are our observations for garbage collection. You can't afford, well, you know this, you can't afford to lose capability tags. And sadly, you know, these legacy C and C++ code bases do all kinds of grungy things with pointers and very often lose tags along the way. So we've done lots of debugging to find those tags and make sure they stay stuck to our references. The nice thing is this, right? The BOEM collector normally looks at all your reachable address space and looks at every word in there and says, this bit pattern could be a pointer to something in memory. So let's assume it is, and let's keep that part of memory alive. But now we have the tags, of course. We don't need to do that. We say, this word has a tag, and therefore it is a capability, and so we need to keep that pointed to region of memory alive. So our conservative collector becomes a precise collector, which means there is an overhead reduction. Hooray for Cherry! You know, normally we're saying Cherry might add some overhead, not too much, especially not to use the right API, but here we're reducing the overhead because there's less that's left on our heap after a collection. There is an issue with seal capabilities because our collector, unless it has an unsealing capability, can't trace the seal capability. So we need to do some kind of patching up there. Oh, and there's a big issue with coalescing. Right. So here's the deal, right? I'm about to kick off my VM and I say, mmap me some space. Bling! And I get back this, what's that, orange space here. Okay. And I start to allocate and I fill up this space here. I do some collections, but eventually I kind of need some more space. So I call to my operating system and say, mmap me some more space. And it gives me some more space. And I have some pink space here. Oh, this might almost be MGE perhaps, different colors, but never mind. Anyway, here's my kind of whole heap here. But if I want to allocate something that is this big, I can't do it because it's stretching over two distinctly m-mapped spaces, and I can't have a capability that stretches across both of them. So I need to m-map another space that's a bit bigger. So we do get some fragmentation in our heap. There is a problem with coalescing. So we do not have, I think somebody called it this morning, an almighty capability. But never mind. Yes, that was a code demo, but we're going to miss that out and talk about runtime code generation because we've only got a few minutes left. Yeah, so we have ported several baseline interpreters, bytecode interpreters to Morello PureCap, one for WebAssembly, one for Python, yeah, and JavaScript core, I think, was ported already, but Jake has been playing with that and working on that. And we're looking now at kind of runtime code generation. People at King's are looking at V8 and also at JavaScript core, and this is very much work in progress, but watch this space. Good. So I'm going to conclude by saying that we think our Capable VMs project does show that Cherry provides defense in depth against VM-based exploits. But I think there are some challenges. And these are the challenges that all our reviewers ask us whenever we try to submit papers. And maybe the challenges that we as a community want to think about very carefully. If you've got the answers, do let me know. Right, so how do we quantify the additional kind of defense, the, you know, extra goodness, the extra kind of security guarantees that our various cherification attempts are giving us? How do we measure performance? Thank you, Cambridge people, for giving us tools and methodologies for measuring performance more accurately, in a more indicative way, perhaps, than we had done previously. And we've adopted the benchmark ABI and kind of using that for our future performance reporting results. But again, I think there's what would you say, some boilerplate text that needs to go with some experimental presentations of Cherry performance. And the third point is, how do we encourage adoption? You know, we're all sitting pretty with our Morello boxes in our office, and maybe some of you using them as kind of nice footstools, and others use office heaters, but whatever they might be, you have lots of machines, and that's good. But, you know, how do we kind of get Cherry to the masses? That's an interesting question. Good. So thank you very much. And if you have any questions, my collaborators will answer them. Ha ha.
Thank you, Jeremy. So are there any questions?
In that case.
Oh, maybe.
I'll just be sure.
yeah, I guess where next with sort of MicroPython?
Yeah, so we're very excited about these new small-scale boards that are arriving. So we've been working with David's Chariot images and playing with those, and we're hoping to get a Sonata board from Canada very soon. And yeah, we hope we'll be running MicroPython in kind of embedded context there.
Cool, great, thank you. Oh, there are some questions.
Compilers do alias analysis. Do you see any prospect of using Cherry to improve alias analysis?
Oh, sorry, Sam. Thank you. Do we see any prospect of using Cherry to improve alias analysis? That's interesting. You're thinking about runtime alias analysis, are you, rather than ahead of time? Yes. 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 So I think you're asking, can the precision of capabilities improve disambiguation and therefore somehow minimize aliasing? That's a nice question. Yeah. Do any collaborators have any answers to that one? Laurie is unconvinced. Thank you. We cannot trace through sealed capabilities. Yeah. So the problem is, right, if a user application says, seal this capability, right, then we don't know how to unseal it when we're tracing. Yes.
Is there any cases where this might actually be a feature in the case of complement problem?
Ooh, have we considered? Say that again.
Have you ever considered this could be a feature that would protect your code or those capabilities?
Oh, I see. There's something you don't want the garbage collector to see, so you seal it. Right. So the only problem there is if the garbage collector can't see it, then it will dispose of it. So yeah, unless you've allocated it in a special way, then it will disappear from under your feet at some point in the future. Yeah, so, but that's interesting. Yeah, I think there does have to be more thought about interactions between user space sealing and allocators and collectors. Yes. And with that, I should retire. Thank you.
Thanks, Jeremy.